Today we're going to look at chapter 10, nuclear physics. In fact, this is the last chapter in the textbook on the topic of physics. From 10, we'll skip to chapter 15 and start dipping our toes in the astronomy. But chapter 15 is coming right up with a share. Okay. And let's make a slideshow. Here we go. All right. Nuclear physics. There's going to be some overlap with chapter 9 and chapter 10. Some of those topics I've introduced already. So, the nucleus of the atom is that central region of the atom where most of the mass, 99.97% of the mass of the atom is located in the nucleus. And the subatomic particles there, we're going to cover in a minute, are positively charged protons, and in most cases, the neutral neutrons. The nucleus of the atom is actually quite important. Phenomena that originate in the nucleus are used for diagnosis and treatment of cancer and many other diseases. So the understanding how the nucleus of the atom works and the nucleus of different elements, certain types of elements that we'll discuss, are essential for the treatment of cancer and other diseases. We also use characteristics of the nucleus to date things that we find in the ground, primarily. And we'll talk about that also. Chemical analysis. If we understand the nucleus, there are certain types of chemical analysis that can only be done with an understanding of the nucleus. Many chemical analyses can be done with just an understanding of the whole atom and how it behaves. But there's some chemical analyses that require an understanding and use of different properties of atoms based on their nuclear characteristics. And of course, energy. Can't leave that out. Nuclear energy and the consequent disposal of nuclear waste are huge issues. We can also form new elements, or new elements can be identified based upon their transmutation, and we'll define that later. But in simplest terms, it's the conversion of one element into another. Radiation from the sun originates in nuclear physics. What happens among the various nuclei in the sun that allows it to radiate such massive amounts of energy. And it's been doing it for billions of years. Something as simple as a smoke detector uses phenomena that originate in the nucleus of the atom. I'll introduce that topic as well. All right, so let's back up a little bit and we'll pick up some information that was also introduced in chapter 9 The Greek philosophers, the ancient Greek philosophers, were the first people to speculate about the basic substances of matter. Aristotle thought that matter was composed of 4 basic elements: earth, air, fire, and water. He was wrong on all counts. There were, however, some thinkers, Leucippus and Democritus in particular, who proposed the atomic theory. In other words, all matter was made of particles that were the smallest particles you could obtain. And we mentioned that in chapter 9 as the discrete theory rather than the continuous. So you could keep subdividing matter down, keep cutting it in half, cutting it in half. Eventually you get to a single particle of matter. That was their atomic theory. Unfortunately, they were in the minority, and it took a couple of millennia before Western science caught up with them and started putting some teeth into this theory. Now, there are 118 elements in the periodic table. 118 elements are known, and each one has a particular symbol. Now, we inherited some of the elements we already knew. Modern chemistry and physics already knew these elements by the time the 18th century rolled around. Unfortunately, the symbols that they were using were not appropriate. Some of the symbols actually denoted elements, and some of them were other substances that we now know as compounds. And their symbols were just all over the place. Alchemists were notorious for guarding their secrets. So when they learned how to do something, it was rare that they would tell anybody else except their apprentices. So exchange of knowledge was not common, and they used whatever symbols were convenient for the individuals. Some symbols came into common use, but they were sort of, I wouldn't say arbitrary, but they were difficult to systematize. There were 2 systems. By the time modern physics and chemistry rolled around, there were 2 systems that were proposed. One was by John Dalton. And you remember John Dalton's atomic theory, which was a masterpiece. It set science on the road to really discovering what matter was all about. And then the other one was proposed by a Swedish chemist named Berzelius. Now, Dalton's symbols were kind of odd. Sometimes they bore some resemblance to the name of the element, like gold, platinum, silver had circles around them. Oxygen was just a circle, so we could say, okay, that must be an O. But hydrogen had a circle with a dot in the middle of it. Nitrogen had a circle with a line through it. So they weren't very systematic either. And besides, there was little room for expansion, because people were already starting to guess that these 36 chemicals, these 36 symbols for elements were not the final story. There were going to be other elements. And fortunately, Berzelius' system won out. Berzelius proposed that we identify each of the elements simply with a letter. Many of them have single letters, like hydrogen, oxygen, nitrogen, phosphorus, sulfur, potassium, had single letters, and they were always capitalized. But when you wanted to name another element based upon its English or Latin name, then the alphabet run out of letters. So he said, okay, we'll just add a second letter. And the second letter would be small. So you'd have a capital and a small together if there were two letters for an element. So helium is He, not H, because H is already taken for hydrogen. And Berzelius proposal won. And fortunately for us, he did, because it's easy to identify the element with this lettering system and to add new elements as they are obtained or discovered, excuse me. Okay. Most of the letters we can identify, most of the symbols we can identify with English, like hydrogen, H, helium, He. But there are a few that are based upon the Latin names, and you just have to memorize them. Antimony is Sb, for stebium, which is the Latin name for antimony. Copper, cuprum, Cu. It's not Co. Co is reserved for cobalt. Gold, Au for aurum. These are all Latin names. My favorite is Pb for lead. Plumbum in Latin means heavy. So that's suitable for lead. All right. So you'll have a few that are based upon the Latin, but most of them can be traced to their English roots. Now, I want you to memorize the symbols for 61 of the elements. 61 out of 118. So it's about half of them. And I've got the next slide will show you which ones I want you to memorize. Here we go. This is a periodic table that I made because I couldn't find one on the internet that was easily modified and so that it would suit my needs. So I just built this one in Microsoft Word. And the ones that are bracketed by red boxes, right, there you go. All these down here, except for that one, francium. Those I want you to memorize. All these across here, and then you've got some here. There's a couple there. There's a couple there below that, and a couple there, and a couple there. Then you have these across here, noble gases, and then a few over here. So if they have a red box around them, notice that indium doesn't have a red box because it's open on the bottom. And thallium is open on the bottom. Polonium is open on the bottom, so it's not surrounded by a red box. And there's a faint pink color to them, if you hadn't noticed that already. These are the symbols of the elements I want you to memorize. And there are two down here in this group. U for uranium and Pu for plutonium. Those are not commonly used in chemistry, but they are in physics. So the best way to memorize these symbols is to make flashcards. Just get yourself a set of blank flashcards. If I can find my set. Let's see. Here we go. You know, what is this? 3x5s, 4x6s maybe. No, 3x5s. Doesn't have to be 3x5s, but they're easy to handle, right? Here we go. And on one side, write the symbol, and then go to your textbook. In the front of your textbook, I believe. Let me check to be sure. Yes, in the front of your textbook is another periodic table. And in this one, the names are given with the symbols. The reason I don't put the names in this periodic table is because they take up too much room, for one thing. Plus, I let my class use the periodic table during exams. And sometimes the question says name You know, what's the symbol for whatever, or what does this symbol represent? And then I don't want to give them the answers, of course, that would be ludicrous. So this periodic table only has the symbols. The periodic table in your book has the names. So you can go through the ones, find the ones that you want, write down all the symbols, and then go to your book and find the names and put the names on the other side. And then use these cards to memorize them. Just go through them one at a time. Maybe look at the name. What's the symbol? If you get it right, put it in one stack. If you get it wrong, put it in another stack. And then when you get finished, take the stack that you got wrong and work on those until you get some of those right in the other stack. And then you just keep working until you got them all done for the first time. Then you go back, shuffle them together again, do it all over again. That's how you memorize the symbols. Now, you'll need to know some of these symbols for chapter 10. And then if you plan on taking the second semester, a third of the second semester is chemistry. And you will have to know these symbols for chemistry. So you might as well learn them now. All right, let's talk about the atom. Okay, first of all, according to Dalton, all matter is composed of atoms. The smallest part that cannot be cut any further. That's what atom means. A for not and tome for cut, not cut. All atoms are composed of 3 subatomic particles: the positively charged proton and the neutral neutron reside in the nucleus. And then all the rest of the space of the atom outside is occupied by electrons that are negatively charged. All right. Sometimes they're called nucleons. So when we say nucleon, it's protons and neutrons. All right. And the protons and the electrons neutralize each other so that if you have exactly the same number in an atom, the atom is neutral. Okay. These are some characteristics. The fundamental charge, one electron has this many coulombs, and a proton has same but opposite sign. Notice that the mass of the electron is very small, but the mass of the proton and the neutron are very small too. The ratio between them is important, right? The ratio between the proton mass and the electron mass is over 1,800 times. So the proton is huge in comparison to the electron. There's a system, unified atomic mass units. Protons are about 1, neutrons are about 1. Right, and since we're not going to dig into it really deep, you can assume that a proton is 1 atomic mass unit, a neutron is 1 atomic mass unit, and the electron is a small fraction of that. Right, 1,837 times heavier is the proton and the neutron from the electron. All right. So we mentioned in chapter 9, the electron was actually discovered by J.J. Thomson, which won him the Nobel Prize in 1906. And he didn't just discover it, but he also measured the ratio of the charge in coulombs of the electron to its mass. And he found out that the ratio was about 10 to the 8th coulombs per gram of electrons. Now, he didn't have the, I don't know if he didn't want to or didn't have the technology available to actually determine the mass of a single electron, but he did determine the charge to mass ratio. So that was a step in the right direction. And it was followed up by Robert Millikan. J.J. Thomson was in England. Robert Millikan was an American. And his experiments actually determined the mass of a single electron. So there it is. And then, of course, I mentioned Rutherford, who discovered the proton and proved the nuclear atom. And then his postdoctoral assistant, James Chadwick, discovered the neutron and characterized that one. And all these guys won Nobel Prizes for their work. They were recognized for what they had done. Okay, so this is just a rehash of the Rutherford's work to prove the nuclear atom. So I won't go over that again. This is just another visual aid. Okay. It does give you some specifics, though. I didn't mention those in chapter 9. So 1 out of 20,000 alpha particles bounced straight back. Okay. The detector saw them pretty near the source. And the only way Rutherford could explain the phenomenon that he observed was that most of the mass of the atom was contained in a very dense, small nucleus. The diameter of the nucleus is indeed very small, 10 to the minus 14th meter. The orbit of the electron is about 10 to the minus 10th meters. So basically what this says is volume-wise, most of the volume is in the orbitals of the electron. So the atom, if you take the atom as the fullest extent of the electron cloud around the atom, then you're going to find that most of that space occupied by the electron is empty. It has a very, very low mass in that area. Okay, so the diameter of the atom is approximately 10,000 times the diameter of the nucleus. And that's what these values represent. Okay, 10 to the 4th difference between minus 14 and minus 10 is 10,000. So somebody calculated this out. I don't know if it's right. I'll take them at their word. In fact, it probably came out of the textbook. If we only had the nuclear material from atoms and just did away with the electrons and then packed all that nuclear material close together, then a ping pong sized ball of nuclear matter would weigh 2.5 billion metric tons. And actually, there are some stars at the end of their life that become packed, dense nuclear material. They're called neutron stars. And they would be that dense. Okay, so you've got neutrons and protons here packed together. The obvious question should be, we already know from our study of electromagnetism, that chapter, that like charges and electricity, like charges repel one another, correct? So with these protons packed so close together, why don't they just fly apart? Right? Because they're all positively charged, they're pushing against each other. Well, we're going to find out that the job of holding them all together, that's the job of the neutrons. The neutrons aren't there just for fun. They're there for a purpose. Okay, so when we write the symbol for any element, I'm just going to use a generic. Okay, there's my symbol for an element. I can do that because there's no element in the periodic table that has an X as its symbol. There are some that have XE. Let's see, xenon is XE. I'm looking for any others. I think it might be the only one. I think it is. So X. Now there are 4 positions around the symbol that are reserved for specific information. Each corner here. All right. The atomic number is the number of Z is the number of protons. So the Z goes here. That's the number of protons. And in a neutral atom, that means you have the same number of electrons. So if you have carbon, you have 6 protons. In the neutral carbon atom, you'll have 6 electrons also. Okay. Now, just as a point of information, what happens if you lose an electron or gain an electron? You have an unbalanced charge, correct? If that electron is added, then you have a negative charge. And if you take the electron away from a neutral atom, you have a positive charge, right? Because you have an excess number of protons, which means you have excess positive charge. That's the only way that you can make an ion, is to add or subtract electrons. What happens if you add or subtract protons? If you do that, you got a different element. You don't have an ion of the previous element. So you cannot make ions with changing the atomic number. Have to do it with electrons. Okay? That's why I put it here in red and yellow. That's a very important rule. Okay, what else do we have going for us? Well, in the upper left-hand corner is called the mass number. It's always a whole number because it is the summation of the number of protons and the number of neutrons. So if we take Z and add the number of neutrons, and that's the way I write neutrons, little n with a 0 on it to show no charge. Then if you add those together, you get A. So if you're given this number and that number, how many neutrons do you have? You subtract this one from that one, and you get the number of neutrons. Okay. So atomic number, mass number. Over here is the charge. If there is any charge, plus or minus, and then you can say 4 plus, 2 plus, 1 plus, 3 minus, whatever the case may be, to designate the charge on an ion. If there's nothing there, then we assume it's neutral. And then the last one is this corner, number of atoms. So if you have more than one of that atom, then you would put the number there. For instance, in that periodic chart, let me go back to it. Here we go. Notice these in the blue boxes, the elements in blue boxes. That designates a diatomic element. What do I mean by diatomic? It means at normal pressure, 1 atmosphere pressure, and room temperature, or near room temperature, could be 0 degrees Celsius, or it could be 20 degrees or 25 degrees. These elements exist as diatomic molecules. So hydrogen would be this, right? 2 of them, they're bound together as a single unit. Nitrogen is this, oxygen is that, and all the halogens, fluorine, chlorine, bromine, iodine, are diatomic. So they would be like this, like that, and like that. They're all diatomic. That's just the way they exist. That's their most stable form. Okay, so let's go back. Let's see, I'll get there eventually. Here we go. Now, if you have these elements combined in a compound, and we'll talk about that in more detail next semester with chemistry, but if you put more than one of them together to make a molecule, like water. Water has 2 hydrogens and 1 oxygen atom together in a single molecule. So that's what that means. All right. Now, what's an isotope? Well, most elements are composed of an atom with a single, they all have the same mass number. But a few of them have a different mass number. So what does that mean? Well, they can't have a different mass number because of different protons, because we already know that if you change the number of protons, you have a different element. So the difference between these values, if you have a different A number up here, it's because of neutrons, either more or less than the most common one. So if you change the number of neutrons, then you have an isotope of that element. Now, we know that there are 118 elements, right? All of them have names now. They used to have some wonky names that were just invented as placeholders, but they all have given names now. And this periodic table that I've given you identifies them all. I'm not sure if your textbook does or not. No, your textbook misses some of them. But I don't have you memorize any of those that have those wonky names. Just the most common ones. Well, there are 118 elements, but there are 2,000 plus isotopes. So that means there are a lot of different atoms with different numbers of neutrons in them. All right. For instance, carbon. The most common isotope of carbon is carbon 12. So if it's like this, right? This is the number of protons. It will have 6 electrons, right? How many neutrons does it have? 12 minus 6. 6 neutrons. Okay. How about carbon 13? It will have 7 neutrons. How about carbon 14? It will have 8 neutrons. Okay. Oh, by the way, isotope means same place. Iso means same, and tope is derived from a Greek root that means place or location. So same place. These isotopes occupy the same place in the periodic table. Why? Because they all have the same protons. So they go in that square. Now, each atom of these different isotopes has a different mass. It's obvious it has a different mass number, so it has a different mass. Chemically speaking, their behavior is almost identical. There are only slight differences. that won't be important to us, either in this semester or in the next semester. For all intents and purposes, their chemistry is identical. And that's primarily due to the fact that they have the same number of electrons in very similar energy levels. I think the presence of the neutron, the extra neutrons in these isotopes may modify those levels that we talked about with the Bohr atom just slightly, but not so much that it would matter for our purposes. Okay, so these are examples, and we just went through it, right? Calculating the number of neutrons. All you have to do is subtract, say A minus Z is the number of neutrons. Now they used a capital N here. I like the little n right there with a zero. Okay, hydrogen has isotopes, right? The most common isotope is the one with one proton and one electron. So you would write it here, 11H. Deuterium is another isotope. 1 out of every 6,000 atoms is deuterium. So it has a proton and a neutron with the electron. Tritium has 2 neutrons and 1 proton. Okay? So when you hear discussions of heavy water is made out of deuterium and oxygen. Instead of an H, we put a D here, right? There's no, there's no element with just a single D, so we're safe. The presence of these different isotopes is significant when we start talking about nuclear fusion as a source of energy. All right, these are just some common isotopes of the different elements, and I've got an exercise. I'm not sure if the lab exercise for this one is this semester or next semester. I have to check that, but you'll have the information if you need it. How to designate these isotopes and how many of them are there. All right, the natural abundance of this isotope of hydrogen is very high. And in most cases, there's one isotope that is the lion's share, right? There's boron, there's carbon, oxygen, neon. There's one exception to that I can think of right now, and that's chlorine. Chlorine has several isotopes, but 2 of them are almost equal in abundance. Okay. Right, so this is just, we've already done these exercises, so I'm not going to spend a lot of time on them. We've got to cover a lot of ground today. All right, so this is just a review of what we've done up to this point. Right, no big surprises there. Now, what's atomic mass? We define the mass number as A. The number of protons plus the number of neutrons is the mass number. Atomic mass is a different concept. Okay, let's see, make sure I'm still on screen there. The atomic mass is not the mass number. They have sort of a second cousin relationship. The atomic mass is empirically determined. It is the weighted average mass of an atom of the element. in a naturally occurring sample. So what do you have in a naturally occurring sample? You have a mixture of isotopes, don't you? And each one of the isotopes, the different isotopes, has a different mass number, right? So it contributes differently to the average mass, right? So this average mass is not an average atom. There's no such thing as an average atom. It's either one isotope or the other. But we determine the atomic mass, this weighted average, so that we can use that information in calculations, in chemical reactions. And what do I mean by weighted average? Well, that means the mass of a carbon-12 atom is more valuable for mass than a carbon-13 or a carbon-14 because there are fewer of them. Right? So the weighted average is going to take into account more the mass of the carbon-12 isotope. It's kind of like determining your grade point average, right? When you're taking a course that's worth 3 credit hours and you make an A for that one, that's 3 times 4 is 12. That's 12 units. If you take a course that's worth 1 credit hour and you make a D, well, that's worth 1. So 1 plus 12 is 13. And then if you divide by 4, 13 divided by 4 is much closer to an A than it is to a D, isn't it? It's a weighted average. So we take the weighted average of the mass of an atom. And for our purposes in this chapter, we're going to focus on atomic mass in terms of these atomic mass units. There's another way to express atomic mass that's more friendly to chemistry, but we're not going to be doing chemistry in this chapter, so we're going to stick with this one, atomic mass units, which is roughly the weight of a proton or a neutron. So we need a standard. We've got to fix those atomic units, mass units, with some standard. So at this time, the international scientific community has settled upon carbon-12 isotope as the standard. So all that says is that the carbon-12 isotope is exactly 12 atomic mass units. That's it. Everything else is related to that. Now, if we average in the naturally occurring abundance of carbon-13 and carbon-14, then we have the atomic mass of carbon, naturally occurring carbon, is 12.011 atomic mass units. Right? So the standard is one of the isotopes of carbon. But naturally occurring carbon, due to the fact we have carbon-14 and carbon-13, heavier parts, they shift the mass upwards slightly. But still, the weighted average is very close to 12. All right. So, if we can't separate these isotopes by chemistry, right, because they behave similarly, we can't do any wet chemistry on the bench that will separate these isotopes. We have to do it with a mass spectrometer. Remember when we were talking about the spectra, the light spectra? White light through a prism, we could spread it into its colors. This is a similar concept, only it uses a different technology to do it, where we spread the different isotopes out based upon their mass. Right, so here's how it works. In this example, we're using neon gas, right? So neon has several isotopes, and they're all mixed together here. They're injected into this cavity that is evacuated. Right? Nothing in there but your neon when you put it in there. And it's sent through this cascade of electrons. So the neon gets charged. It could be negatively charged. I think it's positively charged, though. The electrons knock other electrons off. Anyway, the charge is the important part. It's charged. In fact, look, I can tell from this picture that the neon ions are positively charged because this grid is negative. And what it does is it accelerates those positively charged neon atoms through that grid. It gives them some kinetic energy. And it's so high that when they get to that grid, they pass right through. And they're on their way with that kinetic energy. And then we send them through these double slits to collimate the beam. Remember, just like I talked about in chapter 9, when we're collimating a beam of alpha particles, you have two slits together, and only the ones that are traveling straight will get through both of them. So we have this straight beam of this mixture of neon. Well, you also know that when a moving, we used electrons when we were talking about electromagnetic induction. But ions will behave the same way in a magnetic field. So this field is very strong, and those ions move through here, and they're bent at right angles to the field, just like we discussed in an earlier chapter. Well, guess what? They're all moving with the same kinetic energy, but they're different masses. So the heavier one resists that magnetic field more than the light ones do. Right? The light ones can be bent easier. So here, over here on this detector, we get the separated ions based upon their mass. Okay, and if your detector is calibrated correctly, you can tell exactly what that mass is. Okay, so that's how we separate isotopes. And then the detector, the modern detectors are so fast, they can count individual atoms as they strike the detector. So you can also determine the abundance of each of the isotopes as well, the relative percent amount of each one. Okay, let's review for a minute. There are 4 fundamental forces in the universe. Gravity, we talked about. Newton identified that one. Electromagnetic. Where electrical and magnetic are combined. I think they're combined primarily because we find both electric and magnetic fields in light, and you can't separate them in light. So we might as well keep them together, at least for discussions of fundamental forces. Then there are 2 others. Well, first, excuse me. The electromagnetic force between a proton and electron is very much higher than the gravitational force. So that's the one that dominates in the atom between protons and electrons. If we go down into the nucleus, you find that there are electromagnetic forces that are trying to drive the protons apart. Right? So when you pack them so close together, they try to push each other apart. Well, that's simply based upon Coulomb's law. Remember, force equals Coulomb's constant times one charge times the other charge divided by the square of the distance between them. So if you push them really, really close together, that force is extremely high. So you need a force that will hold them together. And that is the strong nuclear force. It's named strong for a reason. It has to be strong to hold protons together. And notice, for hydrogen, you don't need a neutron. For the most abundant isotope of hydrogen, you have one proton in there. It's all by itself, right? So it doesn't need any way to bind together. But the next one up, helium, has two protons in it. It also has two neutrons. And those neutrons are there to facilitate the binding of protons together in that nucleus through the strong nuclear force. All right. So this strong nuclear force acts over a very short distance. Don't tell me how they determined this. They got physicists that spend their entire lives working on these small problems. So I'm just going to take them at their word. An individual proton is only attracted by the 6 or 7 closest nucleons and repelled by all the others. So, and that stands to reason because the strongest force that's felt among these protons is for those that are closest together. And as you move further apart, those forces diminish based upon the inverse square law, right? So you really only need several neutrons in close proximity to these, whatever, 3 or 4 protons. Here we got 4 identified. We got 3 neutrons together with them that are supplying the mechanism for the strong nuclear force. What we notice is that when the number of protons exceeds 83, and you can find that on your periodic table, what element follows 83? Up to 83 is bismuth. Anything beyond that is unstable, which means the nucleus is trying to tear itself apart. That's what we mean by unstable nucleus. Anything greater than 83 is unstable. And we'll talk about that in more detail just in a few more slides. It undergoes decay. Those unstable nuclei undergo decay so that they can adjust the ratio of protons to neutrons to a level where they're stable again. Now, 3 of these forces are combined together in what's called the Standard Model. The Standard Model incorporates incorporates the strong nuclear force, the electromagnetic force, and a new force, the weak nuclear force, that has been identified acting very short range and is evidenced primarily in beta decay. So we're going to talk about what beta decay means anyway. It happens for unstable nuclei. But those 3, the electromagnetic, the weak nuclear, and the strong nuclear, are combined in a standard model. And so far it works. The problem is gravity gets left out. Because the model, if you try to shove gravity in there, the model falls apart. Now, Albert Einstein was one of the physicists who was working on a unified model for all these forces. So he could get gravity in there also. And this was in mid to later years. You know, he'd already made a name for himself. And somebody asked him why he spent his time working on this thing, because nothing ever came of it. He says, I can afford to work on this problem. I've already made my reputation. I'm financially secure. I can afford to spend time doing this. Whereas a younger physicist has to produce to make a living and make a reputation for himself. So they can afford to work on it, but I can. That's Einstein talking. Okay, so this reviews what we've, the new information that we got based upon expressions of atomic symbols, how we add information to those symbols, and the topic of isotopes. Now we want to go to a topic called radioactivity. Remember we said anything over 83 is unstable. Right? Every isotope of any element that has an atomic number greater than 83 is unstable. Every isotope. Now, some isotopes for elements that have 83 or less as their atomic number, they're unstable too. And what happens is, in order to find a more stable arrangement for the nucleus, they undergo decay and they produce radioactivity. That's how we know they're there and doing what they do. Another name for it, obviously, is radioactive decay. The spontaneous process that nuclei undergo a change by emitting either particles or rays, and rays are light beams. Okay, so when they undergo this decay, they will throw off particles or they will emit radiation. Sometimes both, and sometimes many at the same time. Okay, we have a name for these unstable nuclei. Well, actually, they're not unstable. A nuclide is an isotope. It's just that simple. A specific type of nucleus. So an isotope is, by my way of thinking, synonymous with a nuclide. So when you say nuclide, you're talking about an isotope of an element. So uranium-238 is a nuclide of uranium. Carbon-14 is a nuclide of carbon. Now, if these nuclides undergo radioactive decay, we call them radionuclides. They are radioactive isotopes. Okay? All right. So let's talk about radioactive decay a little bit. The original nucleus, before any decay takes place, is known as the parent, for obvious reasons. And we don't say the product of the decay is a child, we call it a daughter. Don't ask me why, just memorize it. So you have parents and daughters. Now, if the decay requires several steps, so you have a nuclide and then a daughter, and then the daughter becomes the parent for the next daughter. And that's often the way it happens. You go through several steps of radioactive decay before you get to a stable nuclide. Typically, this is not the only ways, but typically in most radioactive decays occur in one of three different ways, or sometimes combinations of the three. One is alpha decay, right? And it's based upon the particle that's thrown off during the change. It's an alpha particle. And I'll describe what that is in just a second. The other is beta decay. There's a beta particle that is thrown off. And then there's gamma decay. Alpha and beta are particles. Gamma is light radiation, very high energy radiation. And these Greek letters, this is the alpha, this is the beta, and this is the gamma. Greek letters. All right, so let's define what they are. When alpha decay occurs, the emission of the alpha particle is actually a helium nucleus, right? So if you take a helium atom and you strip all of its electrons off, you end up with a helium nucleus. And notice, when we're talking about alpha decay, we don't put a charge out here. We know it's charged, but those charges are only important for chemistry. And you're unlikely, and since helium doesn't partake in any chemical reactions, it doesn't matter. But by convention, we leave the charge off. Okay? A beta particle is simply an electron that originates in the nucleus. And they're very high energy. They're moving pretty fast. And in the process of beta decay, a neutron is transformed into a proton. Okay, I'll show you how that works in just a minute. And then the gamma decay is a nucleus that is energetic becomes less energetic when a gamma ray is emitted. And gamma rays are nearly always emitted along with one of these other processes. All right, so this demonstrates that the alpha particle is positive because it migrates toward the negative plate. Gamma rays are not particles, they're not ions, they're actually light. And beta particles are negative because it migrates toward the positive plate. Okay, when we write a decay equation, this is an example of one. This is thorium that is decaying to radium plus an alpha particle. Okay, there's your alpha decay. A beta decay, right? Here's carbon 14 that decays to nitrogen 14. Notice the difference in atomic numbers, plus a beta particle. Okay, notice any trends here. 90 is equal to 88 plus 2. So this number of protons is equal to that number of protons plus that number of protons. This number of protons equals that number of protons plus this one. Since this one's minus, then the sum is 6. Same thing for the mass number. 232 is 228 plus 4. And 14 is 14 plus 0. Right? So we are conserving atomic number and mass number in our decay equations. A gamma decay, for a gamma decay to occur, we use this asterisk out here, which means it's in an excited state, and the nucleus is the excited state. Over here, it's gone, and you have this gamma. Now, this is a case where you only get a gamma decay. And this just states what I've already told you about the summations have to be equal on both sides. All right. So if you were told that a U-238 undergoes an alpha decay, how would you approach this problem? Well, you know what you're starting with, correct? And you know one of the products is an alpha particle. All right. So we know that. So how are we going to fill this one in? Well, there's our placeholder. This one has to equal that one plus that one. So what's this one? 90, right? 90 plus 2 is 92. And this one is 4 from that one, which is 234. Now we want to find out what is X. Go to our periodic table. And the periodic table is arranged in such a way. Let me see. I've got one here, so I don't have to flip the slide back. So let me see. There it is. So notice that from upper right to bottom right, upper left to bottom right, we increase from left to right the number of protons. So you just follow it along until you find 90. So I find 90 at, right, 90 at thorium, right? Here we go. So far, there we go. And there it is. So we can replace this X with a TH. And now we've completed the decay equation. All right. There are more than those 3 types of radiation. I just mentioned these because you might encounter them. We've talked about alpha, beta, gamma. There's also positron. So what's a positron? Well, if an electron is negatively charged, a positron is the same mass as an electron, except it's the opposite charge, a +1. That's a positron. And sometimes we get neutrons emitted, but these usually occur, well, the positron usually occurs with man-made elements. And neutrons usually occur in nuclear reactions. I mean, not just decay reactions, but in things like what you would normally associate with an atom bomb. Neutrons are given off. Yeah, go ahead and close the door. All right. So I mentioned earlier multi-step decays. And this is an example. Uranium-238 is the most abundant isotope of uranium. And it decays to a stable form by a process, these multi-step processes alpha, beta, beta, alpha, and they just keep going down like that. It ends up at lead 206 as a stable isotope. Notice that the mass number keeps decreasing. Sometimes it stays level, right? We've got atomic number down here, and we got mass number here. So this is the one in the lower left-hand corner, and this is the one in the upper left-hand corner. And whenever you have a beta decay, you change the atomic number, right? It goes from 234, well, it goes from thorium to, let's see, what is PA? I don't know if I have that one memorized. Protactinium, no, that's not it. What's PA? Yeah, I got it right, protactinium. And there's the protactinium has one more proton in it, right? That's what changes the element. But it's lost a neutron. It has the same number of nucleons, but the neutron is changed into a proton. Okay, so that's just an example of a multi-step decay process. All right, how do we identify radionuclides? The only certain way to know you have a radionuclide is to measure radioactivity. But there are some trends that have appeared over the years of study of the various isotopes, unstable isotopes. And they answer this question: which nuclides are unstable, radioactive, and which are stable? One pattern is that most stable nuclides have an even number of protons and neutrons. So for instance, if we look at carbon-12, right, we have 6 protons and we have 6 neutrons, even. Or we could take something even, take something bigger. Calcium. We have 20 protons and 20 neutrons, even. While most unstable nuclides have an odd number of protons and neutrons. Well, no, let's let the slides talk for themselves. How about that? For now, we'll just say most unstable nuclides have an odd number of both protons and neutrons. But there's one hard and fast rule, and that has to do with the mass, not the atomic number. If the atomic number is greater than 83, every isotope is a radionuclide. So any element that's greater than 83 atomic number, every isotope of that element will be radioactive. Which means anything above bismuth. Now, there are isotopes of bismuth that are unstable. But bismuth has stable isotopes, and many isotopes of less atomic number are stable. But anything greater than bismuth, 84 or higher, they're always unstable. Apparently, it doesn't matter how many neutrons you have in that nucleus, it's not enough. So we'll look at a reason why in just a second. Or did we already do that? I think we did already do that. Yeah, we did already do that. Since the strong nuclear force is localized to groups of 7 or 8 nucleons, then when you get to a higher number of protons in the nucleus, then you can't pack enough neutrons in close to the protons to make the nucleus survive as a stable entity. All right, so there's one exception to this rule, and that is technetium, which has an atomic number of 43. Technetium is radioactive. Every isotope of technetium is radioactive. In fact, I think there's only one isotope. Yeah, I believe there's only one isotope of technetium, and it's artificially produced. And it's unstable because it has an odd arrangement of protons and neutrons. 43 from 98 is 55. So 43 and 55, they're both odd. So that rule works for technetium. Okay, another trend that we've noticed is when the number of neutrons is less than the number of protons, you have an unstable nucleus. And this is true for almost all isotopes, except for hydrogen 1,1 and helium 2,3. Helium 3 with only 2 protons and 1 neutron, right? 2 from 3 is 1. It's stable, still stable. The nuclide will be radioactive if it is an odd nuclide, except for deuterium, lithium-6, boron-10, and nitrogen-14. Those all have odd arrangements, but they are stable, probably because they have so few protons in the nucleus that an equal number, so few protons in the nucleus, an equal number of neutrons is sufficient to stabilize the nucleus. So let's take a look at these 3 pairs of radionuclides, actually nuclides, and determine or take an educated guess as to which one is a radionuclide. This first one, what I focus on is the number of protons, right? 82 is less than 83, 86 is greater than 83. So it should be radioactive. This one has an even number of protons and neutrons, and this one has an even odd number. But it also has fewer neutrons than protons. Actually, forget what I said earlier. The reason this one is a radionuclide is the difference between the number of neutrons and protons. There are fewer neutrons than protons, so neon 19 is radioactive. Copper. Let's see what we have here with copper. This copper 64 is 35 neutrons and 29 protons. That's odd. And this one is odd even. So I would guess that this odd is a radionuclide. Okay. How many stable nuclides actually are there with various combinations of protons and neutrons? If they're even, we register 160 stable nuclides. Okay. If they're even odd, even protons and odd neutrons, the number of stable nuclides goes down. So we're starting to reach some instability. If they're odd even, you have a similar number. It's actually the same number of radionuclides have odd even arrangement of protons and neutrons, and those are stable. But the odd odds, there are only 4 stable odd odds. So what's the point of this slide? It just shows you that even is the most stable arrangement. Even odd can be stable, and odd even can be stable. But there are examples where even odd and odd even are unstable. But there are very few examples where odd is stable. In fact, only 4. And we showed earlier that these are very small atoms where you have very few protons in the nucleus. All right, let's look at this plot. Okay, so this plot has the number of protons on the x-axis and the number of neutrons on the y-axis. And all these dots, the blues and the reds, represent a unique isotope. The red dots are stable. Anywhere you have a red dot, that ratio of that many protons to this many neutrons is a stable isotope. The blue dots are the unstable isotopes of any of these. And you have quite a few up here. And notice that once you get past 83, which is right here, then they're all unstable. The red line here represents a 1-to-1 neutron to proton ratio. So the first thing I notice about this plot is that the very small nucleus isotopes tend to follow that 1-to-1 line. Not exactly, but rather close. But as you get larger and larger nuclei, more and more protons, you start to deviate from that 1-to-1 ratio. In other words, you start getting more neutrons than you have protons. And that appears to be necessary to stabilize that many protons. An increasing number of protons in the nucleus requires many, many more neutrons to stabilize the nucleus. And it doesn't always work either, right? Because you rise into this region and you find all these blue dots here are unstable nuclei. That's what I detect from that plot. All right. So we mentioned decay of radionuclide, how it changes by usually either emitting an alpha particle or a beta particle or a gamma ray. And as it turns out, it's interesting and important to know how long will that radionuclide stay in its present form before it changes? Right? And as it turns out, we can use an expression that's common to both nuclear physics and to chemistry, although chemists use it in a different form, but it's a similar idea. It's called the half-life. And the half-life is a very simple concept. It's given this expression, T1 half, T for time, and half for half-life, half time. What it means is, it answers the question, how long does it take for the amount of a radionuclide to be cut in half? In other words, you take a mass of radionuclide, and then after one half-life, you've only got that much left. Half of it is left. How long does it take for that to happen, for you to only have half of it left? And it varies from one radionuclide to the other. Now, the reason we have to say it this way is the disintegration of a radionuclide individual atom is, as far as we can tell, a random process. We cannot say that that atom is unstable and in so many minutes or seconds or hours or years or millennia it will decay. We can't do that. So we have to work in, statistically speaking, if we have this mass, then over this certain amount of time, only half of it remains. That's the half-life. The time it takes for half of the nuclei of a given sample to decay. Now, how much will you have left after two half-lives? If you start off with mass, let's just say mass here. This is one column. And this is half-life. Okay. So at 0 half-life, let's just make up a number. Let's say we have 100 grams. Okay. After 1 half-life, however long that takes, seconds, days, years, millions of years, whatever it takes, after 1 half-life, you only have half of it left. How about 2 half-lives? After 2 half-lives, you only have half of this left. After 3 half-lives, you only have half of that left. See the trend? Half, half, half. 1, 2, 3. So that means that if this is half of that, how much of this is that? 1/4. How much of this is that? 1/8. You see a trend? It's 1 divided by n, no, excuse me, 2 to the n value, where n is a whole number, half-life. 1, 2, 3, 4, 5 half-lives. So this is multiplied by the initial mass. So if you go through 3 half-lives, this will be 2 to the 3rd, or 1/8 of that will be left. Okay? So if you actually go whole number half-lives, then this is an easy calculation. It gets a little tricky when you say, well, let's see, if the half-life is 10 days, right? 10 more days, 10 more days. What if it's 22 days, right? You're in between half-lives. Then you need a formula to help you at that. All right. And that's what this thing shows, right? For this real life example, thorium-234, after its first half-life of 24 days, you have 50 grams left. After the second half-life, you only have 25 grams left, and so forth, so on. And this is what the plot would look like, right? There's one half-life, there's a second half-life, third, fourth. So what does that look like to you? It looks to me like mathematically speaking, that's a hyperbola. In other words, this thing is going to keep decreasing and never touch zero. Now, we know that can't happen because matter is finite. You can't just keep going on forever. So probably what will happen is you'll eventually end up with only 2 atoms. One of them will decay in the next half-life, and then the last one will go in the following half-life. Now, you can measure decays with a Geiger counter. And a Geiger counter is just a device that registers a decay at the emission of a decay particle, like a beta particle or an alpha particle. It doesn't measure gamma particles, I don't think. And ideally, if your decay is from one parent to one daughter, and that's it, then the Geiger counter is a good way to measure it, because you know that any emissions are coming from the parent. Now, if you have a cascading decay from a parent to a daughter, and then the daughter becomes a parent, and then you get a convoluted message from the Geiger counter. It's getting decay indications from both this one and from the new parent, and then from the next parent. Okay, so there's a mess. That's a mess. And when that happens, you need to use a different technique to measure the amounts of the products, or what's left over is usually the easiest way to do it. Okay, so how long are the half-lives? How long does it take for half of a substance to disappear? Well, it depends on the radionuclide. Some of them take a long time. And some of them go in the blink of an eye, quicker than that. Like beryllium-8, it's gone in 10 to the minus 15 seconds, half of it. So within minutes, everything you've got is probably gone. Whereas something like uranium-238 takes 4.46 billion years for half of it to go, to change. And indium-115 takes even longer. Billion, trillion. Let's see, 9, 3, no, more than that. So that would be 3, that'd be 4,400 trillion years for indium. Carbon, right, you've heard of carbon dating. We're going to talk about that in a minute. Carbon-14 half-life is 5,730 years. So there are several implications from these differences in half-lives. One has to do with health hazard. What is the effect on the radioactivity of a nuclide based upon its half-life? Well, the faster the radionuclide decays, the more radiation it emits in that time period, right? So if it's emitting beta particles and it decays in 30 seconds, the same mass of this radionuclide compared to this one, which decays once in 100 years, half of it's gone in 100 years, is much less radioactive than the one with a short half-life. That's the first implication. You would get a higher dose rate from the same amount of a short half-life radionuclide than you would from a long half-life radionuclide. Okay. The flip side of that coin is that the hazards of the radionuclide last a lot longer for the long half-life radionuclide. Right? So it may be a low dose environment, but it's still radioactive, right? And there's no lower limit to the dangers of radioactivity. If it's there, it's a hazard. And of course, there's also the type of radiation matters, right? And we'll talk about that in a little further down the line. So hold that thought and we'll come back to it. Okay. Let's take this example. What fraction and mass of a 40 milligram sample of iodine-131 will remain in 24 days? And its half-life is 8 days. So sometimes it's useful to draw a picture or a table in this fact. So if we do that table again, we're starting off with 40 milligrams, correct? 40 milligrams. And time is 0. That's where we start. So the half-life is 8 days. So how much will remain after 8 days? Half of it, right? Okay. What about another half-life? What do you have next? Well, 8 days and then 16, correct? This is one half-life. This is the next half-life. How much remains? 10 milligrams. How about 8 more days, another half-life? That's 24 days, correct? And then we have 5 milligrams left. So, what fraction of this mass is 5? 5 divided by 40? Okay, so that's the fraction. And we have 1/8. So 1/8 of this is left. So that's 2 to the first power, second power, third power, 1/8. 1/8 of this is left over, just like I showed you in that earlier formula. After 3 half-lives. Okay. So, we got another problem. What fraction of strontium-90 produced in 1963 will remain in 2021? All right. So let's do this one. Okay. So we only want to know what fraction remains. Doesn't matter what we start with, correct? So if we start with something here, M0 at 0 time, then a half-life is 29 years, right? T 1/2 equals 29 years. So how many years is it between 63 and 21, right? 20, 21, 1963, right? That's 8, and 6 from 11 is 5. That's it, 58 years. Correct? 58 years. So one half-life is 29 years. How many half-lives is 58? It's 2 half-lives, right? So 1 over 2 to the n equals 1 over 2 squared. 2 half-lives. We've got 1, 2. So 1/4 of strontium-90 remains in that amount of time. Okay? And N here represents the starting amount. All right, finding the elapsed time. So up to this point, we want to know how much remained, either absolute amount or fractional amount. But suppose we want to know the elapsed time that has occurred. If we measure how much you start with and how much you end up with, can you deduce from that the elapsed time? Now we're sort of edging our way toward dating objects based upon their composition and ratio of parent to daughter nuclides. So we're going to use carbon-14 in this case simply because it's very commonly used to date fossils that were at one time in the past living. Right, that's key. Why? Because carbon-14 is naturally occurring in the environment, and when you're living, you take in carbon, all the isotopes of carbon, and your body can't tell the difference. It just uses carbon in its, well, actually plants do. Plants take in carbon and they convert carbon dioxide into simple sugars and then more complex things and store them in their tissues. Well, they keep taking in carbon-12, carbon-14 at the same rate, right? So it's a stable ratio until they die, and then they don't take in anymore. So at that point, the clock starts. So how long ago was it since that plant or animal died? Animal gets the carbon-14 from eating the plants or eating other animals that have eaten the plants. So the ratio is fixed until they die. So let's look at this. Carbon-14 has a half-life of 5,730 years. Okay, we know that. All right, so the question is, how long would it take a sample of carbon-14 to decay to 1/4 its original activity? Okay, so we're going to get to 1/4. So 1/4 is what? It's equal to 1 over 2 squared. That's 2 half-lives. So the first half-life is 5,730 years. Second half-life is 11,460 years. Okay, 2 half-lives. There you go. So how do we know the half-life of these radionuclides? They have to be measured, right? There's no theoretical model that will predict the half-life of any radionuclide. This is all empirical data. You have to measure it. Okay. Now, that could become problematic, of course. If you try to measure something with a half-life of 4.5 billion years, right? So the longer the half-life, the more accurate the instrumentation required, because you've got to detect very seldom emissions. All right, so that's what we mean by monitor the activity of a known amount in the laboratory. If the half-life is very short, then you can measure it with very tiny amounts. But if the half-life is very long, you need huge amounts, because the probability says that not many of those are going to decay over the next days, months, years. And you need to pick up some rate of decay in order to extrapolate to the half-life of a long-lived radionuclide. How do we measure those counts? Well, if we can trust the decay to be one parent, one daughter, then you can measure the decay rate as counts per minute. And Geiger counters in particular are designed so that when a nuclide hits the detector, it causes a current that is given a sound. It's usually a click. So if you have very slow clicks, that's basically background radiation that's coming from all around you. But if they start to pick up and you're moving closer to some sample, then you know the sample is emitting. And with the help of computers and interfaces with the Geiger counter, those counts can be quantified. Even though they're very rapid and they sound like a blur to your ear, then the computer can take the guesswork out of it. Human error. Now, for samples which are short enough lived so that we can, in a reasonable amount of time, measure the actual rate of the counts per minute to drop to half of what they started as, then we can say that is the half-life. Okay. For longer-lived radionuclides, you need a little mathematical wizardry to figure that one out. And I have a formula I'm going to show you in a minute that does just that. Okay, this is what a Geiger counter looks like. You know, it's got, this is the detector, and the incoming radiation will pass through this window, and the detector device is the entire wand. And the radiation will not pass through the outer walls. It only goes through the window. Right? So you aim it at your source. And the environment in here is filled with an inert gas. Argon's a good one. And when the radiation strikes one of those argon atoms, it kicks off an electron. And what that does is it causes the ability of the gas to transmit a signal from the inner electrode, this wire, to the outer wall, which is charged opposite to the wire. And when it does that, then you get a current, and it's amplified through the electronics. All right, so here we go with radioactive dating again. Because the decay rates, the half-lives, are absolute, they're constant for the radionuclide, we can use that as what we would call a nuclear clock. It occurs regularly, just like a clock would tick off seconds. The radionuclide ticks off its half-lives. So the this is the basis for dating objects, either once living objects or minerals which have accumulated radionuclides in their formation, and then were fixed by some natural process, and they continue to decay. The trick, though, is to know or to guess how much radionuclide was present when the clock started thousands or millions of years ago. Okay, that's the real trick in using this radioactive dating procedure. For near-term, short-lived radioisotopes, and to some extent carbon, we have to assume that the mix of radionuclides in the past is the same as it is today. So that sometimes that's a big leap. There are techniques for minimizing that source of error. Right? One of those is, rather than use the absolute amounts, we use ratios of daughter to parent nuclei. And that tends to even things out. All right, so carbon-14 can be used for anything that was once living: wood, bone, even parchment, right? What's parchment? Parchment is a medieval writing material. It's made out of animal skins. Animal skin, they were once living, right? Paper was once living because it was part of wood, or depending on where it was made, it could have been papyrus from Egypt. But as long as it was once living, then it has incorporated radioactive carbon in its matrix, and upon its death begins to decay. That starts the clock. Okay. And this is just in black and white what I was telling you earlier. So this is an example, right? Cosmic rays from outer space produce neutrons in the upper atmosphere, and they react with stable carbon 14 in the upper atmosphere, and they convert over a process of decay. Once this neutron is captured by that, then it forms carbon-14 in the process. Carbon-14 is incorporated into carbon dioxide. Carbon dioxide is taken up by plants. Animals eat plants, so forth, and then they die. And that's when the clock starts. Now, there's a practical limit to how old something can be and still be reliably dated using carbon-14 procedures. And that rule of thumb is about 10 half-lives. And that's the same for almost all radionuclides that are used for dating. After about 10 half-lives, there's so little of the original amount left that our instrumentation can't detect it. It's not measurable. So after about 10 half-lives, which for carbon would be, how about, 40 or 50,000 years would be 10 half-lives for carbon. Right? Anything older than that, it's, you know, really iffy. So here's the formula that helps you, that relates the amount of time that has passed, T, based upon the half-life of the radionuclide and the initial amount ratioed to the final amount. So the final amount divided by the initial amount, and then this factor here, this is called the natural log. Every calculator has a key that will calculate the natural log. Whatever this ratio is, just plug it in your calculator and hit the log key, the LN key, and it'll give you a number. And then you divide by this negative value here, multiply it by the half-life, and that gives you the time that has transpired. Now, the time here is in what units? Well, it's in the same units as the half-life, right? Because this ratio is dimensionless, right? If this is grams and that's grams, grams cancel. If this is atoms and this is atoms, they cancel. The only unit left is the amount of time associated with the half-life. Okay. All right. Now, that was radioactive decay. Other nuclear reactions are possible and often very useful. We know that from radioactive decay, you can change one type of element into another. You can go from one element to another through the decay process. This is called transmutation. Now, it can work either as a natural process, or scientists can transmute elements in their laboratories if they have a nuclear reactor that's particularly designed for that purpose. So, can we possibly add a proton or a neutron? Sure. Neutrons actually work best because if you slow the neutron down enough so that it's captured by the nucleus, then it usually becomes unstable. And then if a neutron decays, giving off a beta particle, it produces a proton, and you change the atomic number of the atom. That makes a different element. As it turns out, Ernest Rutherford, a little later than his gold foil experiment, produced the first nuclear reaction by bombarding carbon-14 with alpha particles. Right? By this time, the alpha particles had been identified. In other words, we knew what they are. We knew good sources of them, and we had identified them as helium nuclei. So this was a planned experiment. He knew that these helium nuclei were going to impact that nitrogen 14. And what did it do? Well, it actually produced an isotope of oxygen. Right? Here's how it did it. Right? Remember, add these together. So 4 plus 14 is 18. right? So this side has to add up to 18. Now, you can't deduce that, right, just from these two. You need more information. So what Rutherford discovered was that hydrogen was being produced out of this process. That was the easiest one to detect. He detected hydrogen of this isotope of hydrogen, and then all he had to do was fill in the blank here. And then, of course, he proceeded to verify it by trying to detect the oxygen too. That's all good scientists don't just go off half-cocked. If they think something is agreed with their preconceived notion, they better not publish it until they're sure. So they go back and they either repeat the experiment over and over again, like Robert Millikan did with his determining the mass of an electron. He used his famous oil drop experiment. Well, I didn't describe it to you, but I think I do in the chemistry section next semester. But he did that experiment thousands of times. Anyway, back to the topic here. So there's the general form of the reaction. And we have conservation of mass, atomic number, and mass number. And this is the reverse of the decay. It appears to be a reverse of decay, right? Instead of emitting an alpha particle, we absorb an alpha particle. Okay? So this is just the general form of a nuclear reaction. You combine these two together and you get these two. So you bombard A with some particle, either helium nucleus, beta particle, neutrons, or protons, and you get a new nucleus here, plus some other emitted particle. In this case, the emitted particle was hydrogen, a proton. That's what this means. That's a proton. Okay. Okay, there's a proton. This is a deuteron. This is a triton. And these are nuclei only, no electrons. And they're very common in nuclear reactions. All right, so let's see if we can figure this one out. There's your proton. It's bombarding this lithium-7 nucleus, and it's emitting a neutron. So if 1 plus 3 equals 4, and this is 0, then this one must have 4 protons. And we look our periodic table, that would be beryllium, Be. And the mass would be 7, right? Because 1 plus 7 is 8, and there's one of them. So this one has to have 7. So it's beryllium-7. Right. Wait for it. There it is. Beryllium-7. Okay. Here's another example. What if we have a deuteron bombarding an aluminum-27 atom? Right? There's aluminum. It's got 13 protons, 27 mass number. Okay. Here's a deuteron. Deuteron has 2 nucleons in its nucleus. One of those is a proton. Right? And we're given that an alpha particle is emitted. Right? So 1 plus 13 is 14, but we took away 2 of them, so this one has to be 12. So we look up there and say, okay, 12 is magnesium. So 12 protons is magnesium. Now, how many neutrons does it have? Well, how many nucleons does it have? 2 plus 27 is 29, minus 4 is 25, right? So this is magnesium with 12, right? There. And 25 mass number, right? Because we had 29 minus 4 is 25. There you go. Now, let me see. Let me keep up with my hard copy here. Okay, I know where I'm at now. Okay. All right. Rutherford's discovery of the transmutation of nitrogen 14 to oxygen 17 was an accident. Well, okay, I don't know the whole story, so I can't say how it actually transpired. I was just speculating earlier. But now we know that one element can be changed into another one, right? What's the old story? Alchemists have been trying for centuries to turn lead into gold. Well, we can do it now. You can make gold in a nuclear reactor. The problem is you got that gold, but guess what? By this reaction, we could take mercury and hit it with a proton and make gold plus an alpha particle. But guess what? It's $1 million an ounce. I think it's cheaper to dig it out of the ground, don't you? Yeah. Now, neutrons are a common particle emitted during nuclear reactions, during certain nuclear reactions. And those neutrons can be used to induce other nuclear reactions. It's kind of like the laser where you stimulate something to happen. Neutrons are good at that. Now, why would a neutron be good at changing a nucleus? It all has to do with charge. Neutrons are neutral. So they can just barrel right through the electron cloud and all the protons and end up in the nucleus. The only thing you have to do is make sure they're not going so fast that they go straight on through before they have a chance to integrate themselves into the nucleus. Right? So what you can produce is a chain reaction. One neutron stimulates a change in a nucleus, and that nucleus, when it changes, emits more neutrons, 1, 2, 3, whatever it takes, producing a chain reaction. So once you get it started, it just continues. But like I said, since they have no charge, they're good at changing nuclei, but they're very difficult to control, right? What are our typical control mechanisms for particles? Magnetic, electrical. But neutrons are not charged. So electrical, magnetic, neither one of them are going to work on neutrons. The best we can hope for is to absorb the ones we don't want to react and try to funnel the rest of them where we want them to go. Or we may moderate them. In other words, if they're going too fast, then they're not going to stimulate a chain reaction. So what we want to do is slow them down. We use moderators, various elements that are good at slowing the neutrons down but not absorbing them. Boron comes to mind. Okay. What's a transuranium element? Anything with an atomic number greater than 92. So if you look at your periodic table, you see that, here it is. Look at your periodic table. Where is uranium? Well, uranium is right down here in this series, this actinide series. So anything that's greater than uranium, heavier than uranium, is here and here. Okay? Those are transuranium elements. So what's so special about transuranium elements? What's special? They're all synthetic. They're man-made. Uranium is the heaviest naturally occurring element. The rest of them are man-made. Even plutonium that was used in the atomic bomb called Fat Man that was dropped on Nagasaki to end World War II. That plutonium was man-made, every single atom of it. Okay. Here's an example where uranium-238 captures a neutron and converts it into neptunium, which is the next element in the series, 92, 93. And it emits this neutron, a neutron decays by way of beta emission, and that converts it into a proton, right? So you increase the number of nucleons by 1 because you've added 1 here, and you increase the number of protons because you emitted a beta particle. So 93 minus 1 is 92. So now you have a new element. And obviously it's radioactive, right? Because it's greater than 83 protons. Here's another example in which we have iron and bismuth being combined. You didn't think we could do that, did you? And what do you end up with? Well, you end up with this one. I'm thinking that's meitnerium. Let me see if that's right. Yeah, meitnerium. But you still have the same balance. Add these together, add those together, same number. Now, reactors are not the only place that elements are formed. Natural nucleosynthesis has taken place since the beginning of the universe. And we're going to talk a little bit about those processes in subsequent chapters. Not in 15, maybe starting in 16 or 17, something like that. But it was believed that these 3 elements were formed at or very soon after the Big Bang. Right? What do I mean by the Big Bang? Well, prevailing consensus among cosmologists, those who study the universe, is that the universe started at an instant from an infinitesimally small something. And just all of a sudden, the universe was born. And it expanded very quickly in the first seconds and minutes. In fact, in the beginning, there were no elements. There were only subatomic particles. And there were even subatomic particles, right? Particles that made up protons, neutrons, and electrons. Then as things started to cool down, you got subatomic particles that cooled down further, then you started to get elements. Hydrogen, helium, and some lithium formed at that time. Now, where did everything else come from? Well, the rest of the elements, from beryllium on up, right? Helium, hydrogen, helium, lithium, then beryllium is the next. It's atomic number 4, up to iron. It's believed that everything up to iron was formed under normal conditions in the core of stars. In fact, it's believed once iron starts to form in a star, its death is imminent. Well, how do we get the heavier elements, right? Iron is what, 26 protons. There's a lot more elements beyond that. Where did they come from? Well, it's believed that the heavier elements were formed in exploding stars, supernovae. That's required because you have very high energy and lots of neutrons. Lots and lots of neutrons that would be required to build the heavier elements. Okay, let's break from that theoretical for a while and look at practical uses of radionuclides. They show up everywhere. We mentioned earlier, and I'm going to rehash some of this stuff, that radionuclides are invaluable for medical purposes. Chemists use them occasionally. Sometimes it's to trace a particular reaction sequence. It's called tagging, nuclear tagging. So since radionuclides behave chemically the way non-radioactive nuclides of that same element, then if you put a little bit of the radioactive nuclide in there, you can track the progress of a reaction by measuring the amount of the nuclide as you proceed through different steps of the reaction. You can use that in biological processes too, to find out where things go. Geology, radionuclides are good for dating. They're good for identifying different types of minerals, which is also helpful in understanding the progression over geological time of processes. In fact, identifying radionuclides was helpful in confirming the theory of plate tectonics. And we'll get to that in the second semester. Agriculture. Radionuclides are used in agriculture. And industrial uses are almost endless. But when you use these radionuclides, you really have to be careful. Special safety precautions are required. In a former life, I was an employee of the U.S. Department of Agriculture, and we had, when I first arrived there, we had a radioactive lab, a lab that was specially set up and shielded so that we could use radionuclides in our research. And we had special precautions. In other words, we had lead-lined cabinets where we could take our nuclides and store them in those cabinets, and there would be no hazard. And when we had to bring them out and use them, we had shielding that we could use. And anytime you worked in there with one, you had to wear a radiation dose badge. And that was yours, your name on it. So periodically that dose badge would be turned in, it'd be sent to a vendor who would read it and tell you how much radiation you had received. Radioactive iodine is useful, particularly for thyroid cancer. Right here, the thyroid gland. Why? Because iodine is preferentially deposited in the thyroid. Remember, a thyroid deficiency produces a condition called goiter. Your thyroid swells if you don't have enough iodine in your diet. That's why salt is iodized. It has iodine added. If you, of course, eat lots of seafood, then you get plenty of iodine that way. But if you live far from the oceans and you limit your intake of seafood, then supplement through iodized salt is valuable. Well, because iodine is deposited in the thyroid, if you develop a cancer there, that's one of the treatments. They give you low-level iodine 123, which decays over time, and it's deposited in the thyroid. And when it gets concentrated in that thyroid, the radiation there is high enough to kill the tumor. You can also be used for measurements as well of the thyroid gland. Americium-241 is completely synthetic transuranium radionuclide used in smoke detectors. Right? So you have this smoke detector in your house, and the radionuclide ionizes the air, which allows for a small, steady current to be passed between these electrodes using those ions. Okay? If smoke is detected, what the smoke does is it quenches the ions that were created, and when it quenches them, it decreases the signal that's passed through that circuit. And that is detected by the alarm system, and it starts a loud racket. This is a discussion of radioactive tracers. Both tritium and carbon-14 are radioactive, and they can be detected easily, and they're used to tag atoms within molecules. Carbon is particularly good for living systems because we're basically bags of carbon in water sacks. And we can trace the reaction pathways of drugs and hormones, for instance, in the body. Find out where those drugs go. You can also use, they don't use carbon-14 or tritium, but radioactive nuclides, you can drink them. In fact, one way is, let me see, what element is that? Strontium, I think. Radioactive strontium. You drink a cocktail and you wait an hour or two, and what happens is your body deposits it in your bones. And then you go lay down under a detector and it scans you, and it picks up that radiation from that molecule, that atom that was deposited in your bones, and it can give you a picture of your bone density. All right, you can find out how old rocks are. You can use it as a tracer in manufacturing processes. to test durability. Right? So you measure the radioactivity of a product, and this incorporated radionuclide will, if it's a situation of wear, then how fast does it wear? Well, the radioactivity will decrease over time as there's more wear. I can imagine they could use that in tires. So you test your tires, you impregnate them with a radionuclide, and then you run them on different types of pavement, and then you test how durable they are. Food preservation, right? You can run your food into a room that's shielded, and then open the shielding and expose the food to radiation. And it's very effective at killing microorganisms. You can use radionuclides to detect explosives and contraband at ports of entry for countries. That's a whole lecture in itself, so I'm not going to waste your time with that one. We don't have the time for it, in other words. Now, we've talked about transmutations, where where the element naturally decays, or you create new elements by adding these particles. But there's another process called nuclear fission. And this often happens with radionuclides that are unstable, and they will split into two, not equal, but large, intermediate-sized nuclei. Uranium-235 comes to mind. The same nuclide that was used in the little boy bomb that destroyed Hiroshima. And usually what happens is neutrons are emitted. Okay, so what do those neutrons do? Those neutrons, when one atom splits, neutrons spread out, they make other elements more unstable, they split, and it just keeps cascading. So that would be a runaway nuclear reaction. And in the process of splitting, the mass of the product nuclei is usually less than the mass of the parent. So where did that mass go? Well, Einstein told us where it went. Right? Einstein said, that's where it went. Turned into energy. Light. Converted mass into energy. So when uranium-236 fissions into two smaller nuclei, it emits several neutrons and releases energy. Now notice that's uranium-236. Didn't I just say that uranium-235 was the fissionable nuclide for uranium? Well, yeah, that's true. But uranium-235 doesn't fission efficiently. Uranium-236 is much better at fissioning. So how do you get that to happen? Well, you need an initiator. You need a neutron source to start the thing going. So once 235 captures a neutron, then it becomes very unstable. So it could either fission into these two products and give you one neutron, or it could fission into these two and give you 3 neutrons. Right? So you could average 2 neutrons per fission. So what about this one? What if that one fissioned into this, that, and what's left over? Well, do you have 92 on both sides? Yep, you have 92 on both sides. How about, so the atomic number for this unknown is 0. How about the mass number? 88,144 is 232, right? 232. So that's missing 4 nucleons. Well, they have to be neutrons, right? They have to be neutrons because the protons are all accounted for. So you would have a neutron here with now wait just a minute. Yeah, that's right. 0 protons, right? That's a neutron, not a proton, so it's 0 here. And then you would have 1 there because a neutron doesn't have 4 mass. It's only got 1 mass. So you've got 1 of these. Well, how do you get 4? You need 4 of them. So when you split this one to get these products, you end up with 4 neutrons. Just like that. Okay? You have to, when you solve these problems, you've also got to consider, all right, am I going to create a new particle that doesn't exist? It's unlikely. So you work with what you know. That's why I said 4 neutrons, not some unknown particle with a mass of 4. Okay, how about this one? Well, let's see. 92 protons, and you have 38 here, and what do you have there? Well, 38 from 92, because this is 0. So 38 from 92 is 54. Okay, 54 protons, which means, let me see, I'm looking at my chart. 54 means xenon. So that should be xenon. Okay, 54 is xenon. How about the mass numbers? Well, 90 from, well, actually 90 plus 2 is 92. So 92 from this is, there's a 4 and a 14, 144. So 54 and 144 would be xenon. And that's what the equation would look like. Okay, 3 important features of nuclear fission, where you split an atom. The products of fission are always radioactive, right? So fission, in and of itself, one fission does not produce stable nuclides. Some of the products have very long half-lives, which means, all right, what are you going to do with them until they decay to a very low amount of radiation, right? You store them in, let's see, what was that place called? Yucca Mountain. So there's your waste disposal problem. Relatively large amounts of energy are produced. I mean, that's why we do it, right? We don't just make bombs. There are peaceful uses for nuclear energy. Neutrons are released, right? So the products are always radioactive, large amounts of energy are produced, and neutrons are released. So that's common to all nuclear fissions. So you need shielding for those neutrons during the process of the fission. And there are some very efficient neutron absorbers. In fact, heavy water is a good one, right? Deuterium oxide is a very good absorber of neutrons. And there are others. Carbon's pretty good at it too. So this chain reaction, which produces a bomb, is called an expanding chain reaction. One initial reaction produces a growing number of subsequent reactions because there's usually more than one neutron produced from the fission. So one neutron causes one fission, and then it gives up two or three, and they each cause their own, and then they each cause, it's a exponential growth. So in the case of U-236, the fission may emit two neutrons, right? And each of those two neutrons hit another 235, and they result in the conversion of that 235 to 236. So you get two 236s out of one, which fissions, makes two each of those, and it just expands from there. This is what it would look like, right? Here's the 235, absorbs a neutron, 236 busts open and makes two neutrons. In this scenario, right, we've already seen that 236 doesn't have to be this way. It can be other ways. But in this case, two neutrons are emitted. If it only emits one neutron, then it's not going to be an expanding reaction, because one neutron goes to the next one, and then just, it's a cascade, and that's all. It'll produce energy, of course, but it won't be an expanding chain reaction. Okay, this is what an expanding chain reaction would look like. Now that's opposed to a self-sustaining chain reaction. A self-sustaining chain reaction is one in which it doesn't run away from you. It's basically under control, either self-control by emitting only one neutron, or by introducing absorbers into the flow so that the chain reaction can be maintained but not get out of control. Right? So if we use 235, there are basically two ways to turn U-235 fission into a self-sustaining chain reaction. All right. First of all, don't put too much of it in there, right? U-238 is not fissionable, but it's the major component in naturally occurring uranium. So if you enrich it only to a certain level, say about 3% of U-235 and the rest U-238, then the 235 is not concentrated enough to expand a chain reaction. Right? There's just too little fissionable material. You also have moderators in there. Moderators do two things. One is they absorb extra neutrons so that you don't get an expanding chain reaction. And they slow down fast neutrons, slow enough so that they can be captured and actually create the chain reaction. So it's a balancing act between those two for the moderators. Now, the concept of critical mass is is what actually creates a fission bomb. Critical mass is the minimum amount of fissionable material necessary to sustain a chain reaction. Now, you can have critical mass of a certain amount to produce this self-sustaining chain reaction, or you can have more than that, in which you'll have an expanding chain reaction, and that would be a meltdown or a bomb. For uranium-235, you need about 4 kilograms, baseball size, of pure 235, and that is critical mass. Subcritical mass obviously means no chain reaction occurs. So subcritical mass will fizzle. In other words, it's not going to blow up. It won't even sustain. It won't be self-sustaining as a chain reaction. And each of the fissionable materials, fissionable radionuclides, has its own characteristic critical mass. Supercritical mass is the one that will expand the chain reaction, and you get either a runaway reaction or an explosion. Now, this description of mass here is rest mass. Right? If you just take 2 chunks, half of the critical mass, and you just bring them and put them together, right? Just slowly bring them together. That's what rest mass is. If, however, you can drive the masses together at some increased velocity and impact them together with sufficient momentum, you can turn critical mass, or subcritical mass for that matter, into supercritical mass. Right? It has to happen quickly. It has to be under huge compression. Rapid compression, like that, will turn a smaller mass into supercritical, and that's where you get an atomic warhead. Now, for Little Boy, they used a gun trigger. In other words, Little Boy was this long tube with its fins out here, and it had uranium 235 here and uranium 235 here, and it had a neutron source right there, something to add neutrons, and high explosive here. And it drove this thing down the tube and smashed them together. And then that's what led to the explosion. That's called a gun type trigger. Fat Man was a different proposition. Fat Man was made of plutonium. Yeah, plutonium-239, I believe. And they weren't too sure about the plutonium. They didn't understand it as well. The physicists in the Manhattan Project that built that device. So that's the one they tested at Trinity. They called it the gadget. And it had to be compressed differently. You couldn't just smash one thing like this into it. They actually had to compress it. So that's why Fat Man had this spherical shape, right? You had plutonium around here, 239. And then you had all the way around it 3 dimensions, you had explosive panels, and each one was wired with a detonator. And they were timed such that they all went off exactly the same time. And they drove this plutonium together, smashed it, they compressed it, and it went off. Reached supercritical mass. Okay. Why is this critical mass a factor? Well, it has to do with the density of radionuclides or fissionable nuclei and the production of neutrons. Right? If you have too much surface area for a particular nuclei, then a lot of the neutrons escape. They don't interact. They don't cause a fission event. So you need something big enough so that the neutrons inside have time to interact with nuclei. So see, the bigger one, you have more opportunities. Okay, I said uranium, naturally occurring uranium is very small amount, 235, about 0.7%. So if you enrich it to in the neighborhood of 3%, you can use it for peaceful purposes to sustain a self-sustaining chain reaction that can be used to create steam and drive a turbine and a generator and so forth and so on. It has to be much, much higher concentration of U-235 to make a weapon. And that's what the Iranians are trying to do now. Everybody knows it. Most political figures are in denial, but eventually Iran will create one of these weapons, and it's a psychotic regime. They will use it. All right. Around 90% U-235 will go supercritical. And I don't have time to explain how they enrich, but it's an interesting story in and of itself. All right, I already described the supercritical process, right? So I'm not going to spend any time on these slides. Except to make note here, remember the neutron source as sort of an initiator, a mixture of polonium and beryllium, radioactive nuclides of polonium and beryllium are good sources of neutrons for triggering the chain reaction. Okay, in a reactor, in a peacefully employed nuclear reactor, you have the fissionable materials in these long rods. And then in between those rods, you have other rods that are moderators. So they can be dropped into place to absorb neutrons or slow them down, as the case may be. And that's how you control the reaction. Beryllium and cadmium are good neutron absorbers. All right. So this is a schematic of possible. This is the type of nuclear reactor that historically was built in the United States. Other countries use different designs. These are your control rods, and this is the reactor vessel, right? So the water enters through these ports, and it goes out these ports. And it's under very high pressure, 300, 350 atmospheres, very high pressure. Under those pressures, water can absorb a lot of heat without turning to steam. right? Remember when we talked about specific heat of water? Well, that was under one atmosphere condition. But if you increase the pressure, then you can keep water as liquid, and you can just keep heating and heating and heating. And it becomes a very efficient heat transfer medium. Right? So here are the fuel rods, and you have the fuel pellets in here, uranium, and they're created in bundles, and then these bundles are stacked, and then there are holes in there, channels in there for the water to go through and absorb the energy from the reaction. And then if you withdraw the control rods, then the reaction speeds up and you create more energy. Well, as long as you've got some place for that to go, water comes in cool and goes out hot, then you're fine. But if something happens to the water pumps where you don't push water through it, then the heat builds up. And either you drop the drop the control rods and stop the reaction, or the reaction goes out of control and eventually burns through the bottom of your containment vessel. So after the heat is produced, everything else after that is just like any other power station. The heat is used to make steam. Steam goes through a turbine and turns a generator, and you make electricity. And this is a schematic. For safety reasons and for design reasons, this high pressure water that runs through the reactor is in an independent circuit. The only thing that's transferred between this and the rest of the plant is the heat. Right? So we make steam in this vessel, and that water then is just run back around through the reactor. Steam turns the turbine, and then the unused steam is condensed, and that water is reused. Okay, let's see. Okay, the coolant water performs two critical functions. Transfers heat from the reactor core to the steam generator, obviously. And the cooling water serves as a moderator, right? It does absorb neutrons. Now, the neutrons that are most efficiently absorbed to sustain the chain reaction are called thermal neutrons. That means they're slow. So what are some potential dangers? Well, depending on the design of the reactor, and nowadays there are much safer designs for nuclear reactors. The problem is public perception of the hazard and government regulation. It takes decades to get a new reactor built. And there are few companies that can invest that much capital and expect a return on their investment, so nobody invests. They just don't put money into it. It's not economical. Not with the current political and regulatory environment. Okay, so you have to control the heat that's being generated by these nuclear reactions. That's one source of danger. You don't want that to get out of control. You have to continuously remove the heat from that core. As long as it's running, if you don't shut it down, you've got to remove the heat. And that means the coolant water cannot stop. It has to keep going, has to keep circulating. And then what happens if you do have a breach? particularly in that high pressure water circuit, right? That's what those huge domed concrete buildings are for. That's not the reactor, that's the containment building. Well, consider this. That water is under pressure at very high temperature. What happens if the pressure goes off? If it springs a leak? The water in that circuit instantly flashes to steam. And it's going to be radioactive. So what do you do with it? Well, you contain it in a large concrete building. Why does it have to be so large? Because 1 liter of liquid water under that pressure will flash to 1,000 liters of steam, right? So if you have, I don't know, let's make something up. 200, let's make it bigger. 2,000 liters of water in the pressure circuit. All of that flashes to steam, that's 2,000,000, or 2 million liters of volume is required to contain that steam. Okay. If we don't control the heat, we could have a meltdown. And the popular description of that is called the China syndrome, right? If that reaction gets out of control, it's believed that the core could melt all the way through the Earth and end up in China on the other side of the planet, which will never happen, of course, but makes for a good movie. Okay, what will actually happen is if it melts through the bottom, if the core melts through the bottom of the containment vessel, then it will interact with groundwater and produce more radioactive steam that then enters the environment. So elaborate safety mechanisms are built in so that the core will automatically be shut down and then cooled by auxiliary water. Now, I mentioned earlier that there are safer reactor designs. They're being used by other countries. And in fact, there are more abundant fissionable materials that are inherently safe to use that are not being used in this country. And that is from political and industry pressure not to use them, right? It has nothing to do with science. The science is in favor of the new, of the unused fissionable materials. But the regulatory agencies and the industrial powers don't want it to happen. So we're out of luck for now. So have nuclear accidents occurred in the past? The answer is yes. The most famous one in this country was called 3 Mile Island. That's because the nuclear power plant was built in Pennsylvania, southern Pennsylvania. I forget what river it was, but the real estate was called 3 Mile Island. It was an island, and I presume it was 3 miles long. This occurred in 1979, and there was the problem was controlled. There was no leakage of radiation to the environment. Chernobyl, however, was a different story. Chernobyl, Ukraine, at that time it was part of the Soviet Union. So it was mismanaged like all other communist governments mismanaged their environments. And that one turned into a real disaster, as did Fukushima in 2011. Okay. 3 Mile Island was the result of an accidental shutdown of the coolant. There was a partial meltdown, but it never left the containment vessel. The steel vessel contained the partially melted core. Chernobyl, however, was a giant meltdown and fire. And that thing is still a problem today, even after the Soviet Union collapsed. They're still having trouble with that one. And lots of people in the cleanup effort are now dead from cancers and radiation exposure. It contaminated most of Europe. Can't go near the place, not legally. The Fukushima accident was actually triggered by an earthquake and a subsequent tsunami. So when the earthquake happened, that damaged the facilities, and it's built on the coast because they need cooling water. But after the earthquake, which happened out in the ocean, a tsunami was produced, and it swept in across the plant and flooded out backup power systems. The end result was that the International Nuclear Event Scale that rates the seriousness of nuclear accidents classified Fukushima with Chernobyl. That was it was equally serious. Only the Japanese did a better job of cleanup. They're still cleaning it up, but they're doing a better job than Chernobyl ever was. Now, let's talk about breeder reactors. Remember, I said that, for example, plutonium that was used in the Fat Man bomb was produced by a breeder reactor. It was specifically designed, the reactor was designed to produce plutonium as a byproduct. So that's what breeder reactors do. They are designed to create more fissionable material. Okay, so it's simply a bombardment of 238 U-238 with fast neutrons that produce the plutonium-239. And then you have to take the reactor core apart and extract the plutonium-239 from that material in order to use it. Plutonium is a nasty, nasty element. Even if it were not radioactive, plutonium is chemically lethal in its own right. And then on top of that, it's radioactive. All right. It takes about 20 breeder reactors running for a full year to produce enough plutonium-239 to run a single reactor for a year. So it's not very efficient. But most of the breeder reactor activity in the late 40s, 50s, and into the 60s, 1960s, was targeted at producing plutonium for weapons design, right? So the US government funded that, which means it didn't matter if it was economical or not. Breeder reactors tend to run at a higher temperature than conventional reactors. So they use a different coolant, liquid sodium, which is a very efficient coolant. But liquid sodium is corrosive, right? So it takes a special design to handle it. Now, we've talked about fission up to this point. Let's talk about fusion. Nuclear fusion is the holy grail of energy production. Fusion is the process of taking smaller nuclei and putting them together to make a larger nucleus. right? Instead of fission, fusion. You know, simple. Simple said, but very difficult to do. At least on the surface of the Earth it is. But what happens is when you fuse these nuclei together, you lose some mass, right? And the mass is converted to energy. The nice thing about fusion reactions is it doesn't require critical mass. You can have as little as you want or as much as you want. Well, maybe not as much as you want, but the sky is the limit. Whatever your technology will support, fusion is possible. In fact, the sun and all the stars, most of the stars, produce energy from fusion. They fuse hydrogen together, helium together, and produce energy from it. Here we go. Here's one example. In the sun, 4 hydrogen nuclei come together to make 1 helium, 2 positrons, and lots of energy. Other examples, right? 2 deuteriums together make a tritium and 1 proton. I should say tritium, 1 triton nucleus. This is a deuterium-deuterium reaction. This one is deuterium-tritium reaction. So several types of fusion are possible. In fact, some are easier to artificially produce than others. So the efforts for harnessing the power of fusion in the laboratory for our scientists focuses on deuterium and tritium. They tend to be easier to manage than pure hydrogen. And that's okay because there's lots of deuterium and lots of tritium in the oceans. I mean, it may be low percentage or low numbers of atoms, but our oceans are huge. So there's really plenty to go around. Now, the problem is that Coulomb's law is still active. When you try to force positive nuclei together, you get a huge repulsive force. So in order to get them to meld together, you need lots of energy just to get the thing started. And pressure. You have to heat the nuclei up to very extreme temperatures. 100 million K isn't unusual. That's easy to do in the sun because it's massive, it's huge, and gravity compresses everything. And when you compress a gas, you get heat. We'll talk about that next semester with our gas laws. At these temperatures, the hydrogen atoms exist as a plasma. In other words, you got separate protons or nuclei and separate electrons. So there's several technical hurdles for making fusion a viable source of energy. You have to increase the density of the nucleons or the protons in that space so that they will fuse. They have to be very close together and highly energetic. Now we've managed to do that by 2 means, one of 2 means. either the use of a magnetic bottle, and that's easy to do because this is an ionized gas, so we can use magnetism to confine and compress. The other way is to use lasers to compress tiny pellets of the fuel. And to do that, you have to very accurately time a pellet dropping, and when it reaches the center of this sphere, all of these lasers fire at precisely the same time, and they hit that pellet, and through photon compression and energy, they cause a nuclear reaction. Needless to say, the startup energy for either one of these processes is extremely high. So we've managed at this point, experimentally, to invest enough energy in the process so that we get more energy back than we put in. Okay, we know that it works now. This inertial confinement is the one with lasers. So we have a fuel with deuterium and tritium together, and they are imploded by these lasers. Research for this type of reaction is done at Los Alamos, right? Same place the Manhattan Project produced the atom bomb, and also at Lawrence Livermore Labs in California. This magnetic confinement is the bottle I was talking about. There's a name for it. It's called a tokamak, which is, I think it's a Russian word. Okay, this research is done at MIT in Massachusetts and Princeton in New Jersey. They're still working on that one. But worldwide, there are 30 operational reactors of this particular design. So everybody's interested in it. And progress is slowly being made. But the economics is still not there. Now, what are the advantages of fusion over fission? Well, for one thing, we've got plenty of deuterium, right? The oceans are full of it. So that the cost of the fuel is practically nothing. The production of deuterium for other purposes during World War II, because it was a good moderator, deuterium was produced then and is still today very economically. That technology is established. Nuclear waste is almost non-existent for fusion. And the radioactive nuclides that are produced have very, very short half-lives. Fusion reactions do not get out of control. You have to constantly put energy into them in order to maintain the fusion reaction. So if anything happens to interrupt that process, the reaction shuts down immediately. And all you have is just some residual energy that can be easily shunted away and cool the reactor. It's not dependent on a critical mass at all. Okay, nuclear reaction and energy. Right, we mentioned Albert Einstein. When he published his theory of special relativity, he introduced the concept of the relationship of energy to mass and the speed of light with this famous equation. Strange as it may seem, he didn't win Nobel Prize for this one. It was, I mentioned earlier in an earlier video that Einstein won his Nobel Prize for solving the problem of explaining the photoelectric effect. Okay, so when Einstein predicted that this relationship E equals mc squared, it has been proven out time and time again. What's the equivalent energy of 1 gram mass? If you can convert a whole gram of mass into energy, what would that energy be? Right? Turns out to be 90 trillion joules. Quite a lot. Same as 20,000 tons of TNT, 20 kilotons. All right, you know what that means? That's the same size of the bomb that was dropped on Nagasaki, Fat Man. Little Boy was a little smaller than that. It was closer to about 15 kilotons. Now, to put things in perspective, the current world energy demand is 7 times 10 to the 17th joules. It's huge and growing. So at this point, most of the energy used around the world is produced from fossil fuels. There is a significant fraction of it produced by nuclear reactions, nuclear reactors, fissions, but substantially more is produced from fossil fuels. And renewable sources of energy, they're nothing. Just a drop in the bucket, and likely to stay that way because they're not economical. Do you need me for something?
Are you still teaching?
Yes.
Okay. I guess we can do it in the morning then. I have to put my monitor back on.
Yeah, we can do it in the morning. Give your arm a rest. All right. It's very simple to find out how much energy is produced in a reaction. All you have to do is measure the amount of mass before and the amount of mass after, and barring any losses to experimental error, all of that mass is converted into energy. This is known as the mass defect. Right? The difference in mass between reactions and products is the mass defect. And if you employ Einstein's equation, you can take that mass defect and find out how much energy it represents. Now, two types of mass defect. There's an endoergic mass defect, in which an increase in mass has taken place during a reaction. Actually, that's rare. In which case, energy is consumed and produces mass. The amount of energy absorbed is the number of atomic mass units times 931 million electron volts, mega electron volts. So you just need to know what's the change in atomic mass units. And for the other direction, where exoergic, in which energy is released, which means mass is consumed and the mass of the product is less than the mass of the reactants. Then you take that mass to find out how much energy is released and multiply the number of atomic mass units times 931 mega electron volts. And then if you want to convert it to joules, there's your conversion factor. All right, so for example, in this reaction, what's the mass defect? Right? You want to, for the mass defect, all you have to do is look at the mass number, right? 236, 88 plus 144 plus 4 times 1 is 4. And in order to do that, you need to know the exact, see, this is the mass number, and this is the units of the mass relative to that. Remember, because the only one, carbon-12 is the only one that has exactly 12 units for its 12 nucleons. These 236 nucleons actually are 236.04556 units. So this 88 is actually 87.91445. So you have to know the exact value represented by these mass numbers. And when you do it that way, add them up. The total mass on the left is this value. Total mass on the right is this value, a little bit less. So the mass defect is this, right? A fraction of 1. Multiply that times 931, and the energy released in this single reaction from this nucleus to that nucleus to that nucleus to those neutrons is 162 million electron volts of energy. And then, of course, if you have more than one nucleus, you can multiply it by this value and find out how much the total is. All right, so that was a fission. Let's do a fusion. Using the same logic, this one plus that one, how much different is it from this one plus that one, right? So there you have a change of 0.0188 units. So that's 17.5 mega electron volts of energy released in this reaction. That seems less than the other one. But notice that in the previous reaction, these are huge atoms, large mass that has to be maintained to get that much energy out of them. If you use these, they are very light atoms, and you can fit a lot of them together. So as a practical matter, you can actually get more energy out of this reaction than you can out of the fission reaction, because so much space is taken up, mass and space is taken up by those huge atoms. So when it's adjusted for volume, this reaction is much, much more efficient. Okay. And that's what this statement says. Kilogram for kilogram, more energy comes from fusion than from fission. So 1 kilogram of U-235 fissioning is equivalent to 2 million kilograms of coal burning. Whereas 1 kilogram of deuterium releases enough energy for the burning of 40 million kilograms of coal. 20 times as much energy based on mass. Now, what does this chart show? This is on the x-axis is the mass of the mass number of the nucleus. Right? Here we go. Higher mass to the right, lower mass to the left. Relative stability of the nucleus. So the higher the number, the more stable. So fission is going to go from right to left, right? You're going to split these atoms for a more stable, to be stable from here to here. The most stable is iron. You can't get anything from iron. That's sort of the anchor point. But if you go from deuterium and tritium together, fusion, then you get helium. That is a huge jump in stability and a consequent release of lots of energy. So anytime you go up the curve, either from the right or from the left, you are creating a positive mass defect that is converted into energy. Should I say positive? Negative mass defect, actually, because the products have less mass than the reactants. And that means a release of energy. Okay. I said all that stuff before. So there you have it in black and white in print. Let's see, we ought to be coming down the home stretch here. Got a few more slides. What are the biological effects of radiation? All right. The worst possible radiation that can impinge on your body is ionizing radiation. That is high enough energy to cause the formation of ions in your cells. Those are extremely hazardous. And in fact, ionizing radiation has its most detrimental effect upon the nucleus of the cell. It damages genetic material. Alpha particles can do that simply because they're massive. Beta particles can do it because they're negatively charged and moving very fast. Neutrons are very bad for that because they can go right through most shielding. Well, most of the type of shielding you would be wearing, like clothing and skin. Gamma rays are bad, but they're light, right? So light, certain things will block light, and X-rays too. Those are all ionizing radiation. Now, some of these can be produced by non-nuclear actions. X-rays in particular can be produced by non-nuclear reactions. Gamma rays are produced by nuclear transitions only. They can harm or kill living cells, and they're particularly dangerous if they affect reproductive cells, right? Because they will cause mutations. And very often, any children that are produced from cells that have been affected will not produce viable embryos. In other words, spontaneous abortion is likely. But if they do make it to childbirth, and they will have serious defects. The really insidious nature of ionizing radiation is that you can't see it, you can't smell it. For the most part, you can't feel it unless it starts to burn you, right? It feels like a sunburn eventually, but by that time it's too late. You can't taste it, right? So you don't know it's there unless you have a specially designed detector. Film badges like we used to wear in my lab when we worked with radionuclides are commonly used. But they only tell you afterwards that you've been exposed. So these effects can be classified into two forms, and I've already talked about them, but I'm going to name them now. Somatic effects. Those are damage to somatic cells, everything but your reproductive cells, right? The cells that lead to sperm or the cells that lead to ova, eggs. Everything else is somatic. And they have serious impact on the individual, right? If you get enough radiation and damage to somatic cells, it'll kill you. And it's not a pretty sight. Genetic effects can occur if your reproductive cells are affected. And in that case, you get generational effects. Okay, how do we measure this exposure? The standard unit of measure for radiation effects on biological systems, humans in effect, is the REM, which stands for Roentgen equivalent for man. Roentgen is a unit of radiation, but it's been prorated in such a way that it can be used to determine its effect on a person. So in that respect, it takes into consideration both the type of radiation, what kind of ionizing power does it have, and its effect on humans. So in a year's time, the average human on the surface of the earth receives 0.2 of a rem per year. Okay, just from natural sources. People who spend a lot of time at high altitudes, flying airplanes or transporting themselves from place to place at high altitude in airplanes, are exposed to much higher levels. And astronauts, even huge amounts, potentially exposed. So they have to be very careful. All right, so what are the sources of exposure? Right? Believe it or not, over half of the exposure, and by the way this pie chart is built up, the natural sources of radiation are in this tan section, and the man-made sources are in the purple section. So 55% of our exposure comes from radon. Radon is a radioactive noble gas, which is constantly seeping up from the earth below. That's why, more so in some places than others, the accumulation of radon in people's basements is an issue. And they may install ventilation units that keeps it from building up so that it doesn't seep its way up into the living space of your home. Soil and rocks, about 8%. I wouldn't separate that one out because radon, the source of radon is soil and rocks. You get some exposure from internal, right? If you take things into your body that are radioactive as a natural process of your biochemistry, then you'll get some exposure there. Cosmic rays are very high energy particles. They're called rays, but they're not light rays. Cosmic rays are high energy particles that come from outside the solar system. Medical x-rays are a contributing factor. Nuclear medicine, yeah, most people don't experience that though. Some consumer products will have radioactive count to them. In fact, I remember years ago, we were importing dishes, cups and dishes from Mexico. And they were using a red paint. That's a different story, excuse me. Red paint is laced with mercury. They were using a type of glaze in their pottery that was radioactive. I don't know what source it came from, but eventually we got rid of them. It didn't import them anymore. Okay, so you have these natural sources. And for those sources that are outside the Earth, high altitude is a bad thing. So if you live at very high altitude, like Denver, Colorado, or Nepal, or very mountainous regions, then you receive a higher dose of cosmic radiation than people at sea level. Bedrock, of course, produces radionuclides that can be ingested if they make it into the food chain. Carbon-14, obviously. Potassium-40 is another common radionuclide. It's a natural source. There's radon. I don't know where they get this number, but it's estimated that radon causes between 10,000 and 130,000 lung cancer deaths per year in the US. You know, that's a pretty wide margin. So I think there's a lot of guesswork there. But it is there and can be measured. And it's a serious threat. Any type of radiation is a serious threat. There's no lower limit. Anthropogenic sources, medical x-rays, televisions, maybe. Not so much anymore. When we used to use televisions as cathode ray tubes, you know, the big heavy things that were this deep, they produced a shower of radiation on you while you're watching them. Because they're basically an electron gun, firing electrons at a phosphorescent screen on the front. So if the screen didn't catch all the radiation, then some of it leaked into the room. So that's possible. But flat screens now, they're perfectly safe. What they may emit is frequencies of light that affect your brain function. But it's not radiation. Tobacco smoke, right? Tobacco is a living plant that takes up radioactive isotopes from the environment, and then you take them into your body in the smoke. I'll say more about that in just a minute. Nuclear waste. Yeah, it's localized. It may be hazard to some areas, but it's basically avoidable. Coal. Coal was once living, and it contains radioactive isotopes. Oil. And when these things are burned in fossil fuel plants, those isotopes are sent in the atmosphere. And there's some household products that also are radioactive. I compiled this list. There are no nuclear power plants in West Virginia. You probably already knew that. Kentucky doesn't have them either. My guess is that Kentucky and West Virginia are just have sufficient amount of coal that there's no need for nuclear. We got plenty of coal handy. Coal-fired power plants are, the technology is well known and becoming cleaner. So we just stay with what we got. West Virginia and Kentucky definitely. Maine doesn't have any power plants, nuclear power plants. That's probably because they're a bunch of leftists and don't believe in nuclear energy. Delaware, Rhode Island, Indiana, Oklahoma, none of those. North Dakota, South Dakota. These places have lots of oil. Oklahoma, North Dakota, South Dakota, Montana, Wyoming, Colorado, New Mexico, Utah. All these places are developing oil resources. At least they were before Biden took office. Now he's trying to shut them down. Idaho doesn't have any nuclear plants. Nevada doesn't. Nevada got all the power it needs from the Hoover Dam. Oregon's got hydroelectric power. It's quite sufficient. Let's see, this is Alaska. Alaska doesn't have any nuclear power plants. It'd be kind of hard to maintain one up there. Besides, Alaska is an active seismic region. A nuclear power plant up there would be asking for trouble. And Hawaii doesn't have any. Hawaii ought to be, in some places, open to geothermal energy. Anyway, those states don't have nuclear power plants of any kind. So, remember the rim. What kind of exposure will produce certain effects? These are probable effects, not guaranteed. Everybody, all individuals, there's a range of response. But in general, anything less than 25 rem dose, short-term effect is really no detectable effect. 25 to 100, temporary decrease in white blood cell count. So that's not too bad. 100 to 200, you're going to lose your hair and feel nauseous. 200 to 600, diarrhea, hemorrhaging, possible death, right? Especially if you have pre-existing conditions that weaken your immune system. If you get more than 600 rem dose at any one time, you are dead. And that's a guarantee. There's no statistics there involved. You will die. So what are the long-term cumulative effects of radiation exposure? It's really not fully understood. The most likely common long-term somatic effect is increased likelihood of cancer. Just like repeated exposure over the years to sunlight, to your skin, is you run a higher risk of developing skin cancer. It's a type of radiation. Let's see. Marie Curie. Everybody's heard of Marie Curie. She was a pioneer in the study of radioactive materials. And her work with them eventually killed her. Now, I'm pretty sure that this leukemia that she developed was not a genetic predisposition. That was created by radiation. Now, what types, how can you protect yourself from these radiations? Well, neutrons will go through anything, right? You need some pretty heavy shielding for neutrons. Gamma rays are very effective at penetrating clothing, as are X-rays. Beta particles, these electrons, they can be stopped by a thin sheet of paper. And alpha rays can fairly easily be stopped by your clothing. Certainly, a layer of plexiglass is what we used for working with alpha and beta emitters in the laboratory. The real danger to these alpha and beta emitters, and for the gamma emitters as well, is if you actually ingest the radionuclide, then it's inside you sending radiation out into your body. That's the danger. So smoking takes those radionuclides. They may be small amounts for each cigarette, but over the years, you build up concentrations of radionuclides in your lungs. They go in there and they stay there. Now, nobody knows for sure what causes lung cancer from smoking. It could be from the chemicals, right? They will damage cells, but certainly to be considered is possible ingestion of radionuclides. All right, these are important equations. This one that I showed you earlier will be very useful when you come to the laboratory exercise on half-lives and radioactive nuclide used for dating things. So keep that one handy for that lab. That's it for chapter 10.